All right, gang, the purpose of this video is to transition from confidence intervals for proportions to, see if this will get a little clearer, to confidence intervals for means. So much like what we did for confidence intervals for proportions, we used p hat to estimate p. This was unknown. This was given in our sample. So with means, we're going to use the same concept. We're going to use X bar to calculate mu. So X bar is the value we get from our sample. We're going to use it to estimate a value, a population mean, which is unknown. So when we have categorical data, we perform proportion confidence intervals. Like 72% of people believe in ghosts. Well, why is that categorical? Because the 0.72 is clearly a number. Well, believing in ghosts is categorized as either they do or they don't. So we get a percentage of the proportion. So categorical aligns with proportions and quantitative variables align with means. Now, in general, a confidence interval, and in this class, you're going to learn three different types of confidence intervals. You're going to learn the ones for proportions, you're going to learn the ones for means, and you're going to learn at least one when we circle back to correlation and regression. I haven't decided yet how deep I'm going to get into that, so you're going to learn at least one, maybe two. But in general, confidence intervals have three parts. They have a point estimate. Now for proportions, this is p hat. Then they have plus or minus a critical value. For proportions, this was a z alpha over 2. And then you have your standard error for proportions. This was the square root of p hat times 1 minus p hat over n. All of it was under the square root. Now, as we transition this from just being kind of in general to a confidence interval for means, you would think that the point estimate would be X bar, which it is. You would think that the critical value would be Z alpha over 2, which it is not. I'll explain that later. And you would think that from the central limit theorem, that the standard error would be sigma over the square root of n. Well, it's not. All of this stuff over here, which we should know by now, is called our margin of error, is different when we're estimating means and not proportions. So just hang on. Let me try to teach it to you. All right. So what happens when sigma is actually known? When the population standard deviation is known, which is very, very, very rare, we can proceed with this confidence interval formula. But rarely will, and think about it, to calculate the population standard deviation, you have to have the population mean. The formula is you sum up the values minus mu, divide by n, take the square root. Well, it's kind of goofy to think that we're going to have sigma when mu, be able to calculate sigma when mu, which is part of the formula, is not known. So typically, it's extremely rare that sigma is known. And what we do is we use the sample standard deviation as an estimate, so the z distribution is no longer appropriate. So what we end up getting, we end up getting this t distribution, which I'll get ready to teach you in just a second. So this up here, we no longer have a z critical value. We have a t critical value, and we no longer have this value. We have the sample standard deviation. Because of this substitution right here, substituting the sample standard deviation for the population standard deviation, we have to use a different distribution to calculate our critical value. What is that distribution? It's the t distribution. Now, the z distribution has mean 0, standard deviation 1. To complicate matters a little bit, the t distribution has mean 0, but the standard deviation of the distribution will vary according to sample size. Trust me, just give me an opportunity to let you to teach you this stuff. I think you'll see that it may be even easier than the z distribution. Again, if you'll give me an opportunity to teach you. Another little caveat to this is as n gets large, And I'm talking not large, 34. I'm talking about up around 1,000. The t distribution actually becomes the z distribution. So that's just one of those things that one of those things you might just we've all got this trash can of useless information. That might be where you would want to store that. Well, it's actually not useless, but it's not like gonna save you from a deserted island or something. Uh, so instead of one z distribution, which has mean zero, standard deviation one, uh, we have a family of t distributions. We have many t distributions dependent on a certain thing. So confusing, yeah, a little bit. But again, let me complete uh, the presentation of the t distribution. So if there's a family of them, which one do we use when we're calculating our confidence interval? Well, it's easy. We depend on what's called the degrees of freedom, abbreviated DF for obvious reasons. And the degrees of freedom are very easy to calculate. We just take our sample size minus 1. So as long as you can subtract by 1, you can find degrees of freedom. So if we have a sample where the sample size is n equals 67, then our degrees of freedom are 66. And we use the t distribution with degrees of freedom 66. It's going to become really, really, really clear once we dive into stat crunch. So therefore, we're going to get a different critical value for the same confidence interval percentage when our sample sizes are different. Now, let me illustrate this. So let's just say that we are focused on estimating a population mean, and we are set on using a 95% confidence interval. Now, remember, if we're using a 95% confidence interval, then our alpha is 0.05, because again, 0.95 plus our alpha has to be 1. And then alpha over 2, for obvious reasons, should be 0.025. Okay? So when our sample size is 10, our degrees of freedom will be 9. Our T critical is 2.26. When our sample size is 35, our degrees of freedom are 34. Our T critical is 2.032. When n is equal to 100, degrees of freedom 99, and so on and so forth. Now, the elephant in the room, well, one thing I want you to notice that as our sample size got bigger, our sample sizes got larger here. What happened to this T critical? And these are T alpha over 2. Well, they get closer and closer and closer to 1.96, don't they? Which, I told you previously that the t distribution will get closer to the z distribution. Actually, it becomes a z distribution when we get sample size larger. Now, that's kind of interesting, again, to tattoo to the brain and store it in your trash can of useless information. But for practical applications, we don't be concerned about that too much. All right, gang, so how do we come up with this 2.262 and 2.032 and stuff? So we go to our calculator, and instead of coming to normal, we go to our t calculator. Why? Because it's a t distribution that we're using. Now, notice, well, I thought that would, all right, that's cool. Y'all got better eyes than I do, probably. Notice it asks for degrees of freedom. So for the first problem, degrees of freedom is going to be equal to 9. We're going to need above, and I want my area in the right to be 0.025 for reasons I've explained in previous videos. Notice 2.262 are the out to 3 digits. Degrees of freedom 34, 0.025. Oh, there it is. Cool. Greater than, our T critical is 2.032. Degrees of freedom 99, 0.025. Our T critical is 1.984. Bump the sample size up to 750. Our degrees of freedom will be 749, 0.025 in the right tail. Our T critical is 1.963. Now, let's say just for just an example, let me just slide it right in here. If our sample size was 64 and we want a 90% confidence interval, how do we calculate it? Well, alpha is going to be equal to 0.10. Alpha over 2 is 0.05. So it was a 64. So I know my degrees of freedom are going to be 63. I know I need above 0.05. 1.669. All right, it's that easy to do. All right, let's put this stuff to work. So I'd like to estimate the mean IQ of all students at an extremely large university due to the high cost of administering IQ tests and the length of time. We'll select 11 students. We give them all an IQ test, measure their IQs, and we find out that the mean IQ for these 11 students, which is our X bar, obviously, is 108.6. The standard deviation, which is our SX, is 11.8. Construct a 90% confidence interval for mu. Well, a lot of this is just plug and chug. The X bar, insert 108.6. Our standard deviation, insert 11.8. Our sample size, not to be confused with degrees of freedom, right, is 11. And then we need to calculate the T alpha over 2, and we're going to see it's 1.812. Let me show you how we do that. Go to calculator, go to T. Our sample size is 11, so our degrees of freedom are 10. We always want above when calculating these, and we need not 0.5, but 0.05. 1.182, so that's the value that I put right here. Now, the next thing I do is I always do my negative first. So 108.6, I'll tell you what, I actually did this on the calculator. Let me just show it to you. So I put in 108.6. I always put the negative in first because it goes first in the interval. Uh, an interval, this would be pretty goofy to do like 8.2. Remember, an interval is on the interval, these are negative numbers, these are positive numbers. An interval, the left endpoint has to be less than the right endpoint because it's an interval from this scale, okay? So don't do goofy stuff. So I put in the negative first because it goes first. I put in the positive next because it goes second. All right, so my estimate or my confidence interval is 102.5. I'm sorry, 102.15 to 115.05. Now, you probably know what's coming up next, right? If there's a way that we can do this just like we did confidence intervals for proportions on Stack Crunch, then there's probably a way we can do these in Stack Crunch for means, right? Well, you're exactly right. So I go to Stat, and I come down to T-Stat. Now, why do we think it's called T-Stat? Well, it's T-Stat because we're using what's called a T confidence interval, because we use the T distribution. So we come to one sample, and I don't have my data. I've just got the summary stats. So I choose this. So the sample mean is, 108.6. My sample standard deviation is 11.8. The sample size is 11. Need to come down to the confidence interval. We need to make sure that we make the change to a 90%. And I want to show the critical value, although we already know what it is, but it'll just kind of confirm our previous work. All right, so I go directly to the last two. So the lower limit, the left limit, is going to be 102.15, which we found right here, and 115.05, which we found right here. Notice our critical value, our T critical of 1.812 is provided right there. So this is the point estimate. The standard error is what you would get if you divided 11.8 divided by the square root of 11, right? And our degrees of freedom, are, of course, are 10 because 11 minus 1 is 10. All right, gang. I could go on. I'll tell you what. Let's call it a video. All right. Take care.